Okay, without further ado, I'm going to talk about the topic of gravitational entropy and the large-scale structure of space-time. Oh, thank you, Haidar. I agree with you. Actually, my name means the Turk in Ukrainian, Turok. And so my family originated from there. So I do feel a profound connection with the people there. Now, gravitational entropy. I will talk about something I think very surprising. Latham and I found an extremely simple and surprising explanation for the large-scale geometry of the universe. And as you'll see, the mathematics is really quite elementary and very few ways to avoid it. But the conclusion we reach is the opposite of what people have believed for the last 40 years. The conclusion we reached is there's no need for any mechanism to explain the flatness, homogeneity, and isotropy of the universe. The laws of thermodynamics do that already. So it's kind of a shocking conclusion, and very much in the spirit of what we've been trying to do, which is to re-examine the fundamental questions and problems in cosmology from the point of view that maybe there are, after all, simple solutions just using the known laws of physics. Theoretical physics for the last decades has been inventing all sorts of additions like extra dimensions and branes and strings and so on, and these may all turn out to be unnecessary. Now that's also a controversial statement, but one I believe in. But at the end of this talk, I'm a model of the cosmos in which one can actually calculate all these things exactly. So I think string theory and holography will turn out to be very valuable, if only as a toy model within which one can examine these questions very precisely. Okay, so I will continue with the next slide if I can figure out how to change slides. So can you see that slide?
Yeah, that's fine.
Made the universe in this peculiarly simple state that on large scales, the geometry of the universe is consistent with Euclidean geometry and also with very precise homogeneity, isotropy, as well as flatness. And this is a very special geometry, and here is his picture of the maker putting the universe in this special state for some completely inexplicable reason. Now, if our explanation is correct, it's not so inexplicable. It's actually a beautiful success of quantum theory and gravity, and Einstein's theory of gravity, and the ideas pursued by Stephen Hawking on the entropy of black holes, which is what we generalize to get the calculation of entropy. So in the same way as we're not surprised that the gas in a room is more or less homogeneous, that's the maximum entropy state, we perhaps shouldn't be surprised that the universe is also very simple on large scales. Now, let me give you an analogy. If you walk a short distance from where you live or work, walk around on the surface of the Earth, then for all intents and purposes, it is flat because the distance you're exploring is rather small compared to the curvature radius of the Earth, around 10,000 kilometers. So if you only walk, say, 10 kilometers, you're not going to notice that the Earth is curved. Now, this picture taken from space shows that the Earth is remarkably round and smooth. I mean, it's really like a polished marble. And one explanation for that might be this, that you needed some mechanism, in this case, a Scandinavian giant, to flatten the Earth and polish it. It's not a very scientific one, but that I would say is really the analog of inflation. You know, you invent some mechanism which serves to make a universe like the one you want. A better explanation in the case of the Earth is the following, that the Earth is large, it has about 10 to the 50 atoms. And secondly, there's gravity, which pulls the matter inwards. And there's dissipation. So if you drop a stone, or if a mountain collapses, a cliff collapses, it doesn't rise up again because of the dissipation. And gravity plus dissipation allow the system to relax into the into the state of lowest free energy. And the laws of thermodynamics come in, and basically what happens is that it is vastly more favorable in entropy terms to share that gravitational potential energy in some more random geometry, to share that potential energy, to convert it into heat. And the heat is just the thermal motion of the atoms making up the Earth. And so this is why the Earth is so round and smooth. It's that is the most probable state according to thermodynamics. Now, actually, there's some beautiful recent evidence in favor of this picture, which is when you ask, how did the giant mountain ranges form in the Earth? Turns out they all formed just after life formed. Life filled the oceans, plankton. They absorbed the carbon dioxide. They settled to the bottom of the oceans when they died. And there was a layer of graphite, a very thick layer of graphite formed about 2 billion years ago. And graphite is a wonderful lubricant. So it turns out that when the continental plates collided, when there was graphite present, they didn't just grind each other to dust. They slid one above the other. And it turns out about 20 of the greatest mountain ranges of the Earth were actually created in this way. So this is evidence that when the friction was removed, mountains could form. Now, let's talk about the cosmos and gravitational entropy. So, as I'm sure you all know, Stephen Hawking and many others developed the subject of black hole thermodynamics. Hawking showed that a black hole has a temperature inversely proportional to its mass, and then that there is an entropy of a black hole, which is proportional to the square of its mass and to its area. These are the units I'm going to use throughout the talk, that m Planck squared is 1/8 pi g. So we're interested in the entropy of the cosmos, and the nearest anybody had come before our work to calculating that entropy was for de Sitter spacetime, which is not a bad approximation of today's universe in the future at late times, because the dark energy will dominate to the future. But it's a very poor approximation of the past. In de Sitter spacetime, the universe essentially bounces. It has positive curvature, and the cosmological constant is repulsive, and so it's more like a bouncing ball, that it comes inwards and repels and goes out again. So here too, Hawking and collaborators found a temperature, and they also calculated the entropy. In this case, it's just a number, which is inversely proportional to the density in the cosmological constant, or dark energy, and turns out it's 10 to the power 122 for the observed density of lambda. Now, actually, the way Hawking and others calculated this was to use the Euclidean path integral. So it's a very formal approach to quantum gravity, and has its issues, but in any case, this is how it's done. And it's a very simple calculation in principle, because it's kind of obvious that the solution to Euclidean Einstein equations with a cosmological constant is just a force sphere. That's the solution of greatest symmetry, and it is a solution. It has a certain Ricci scalar, which is positive, has a certain volume, and basically you just calculate the Einstein action, plug those two numbers in, and you find the answer I gave. So so this IS, I call, it's the Lorentzian, it's the exponent in the real-time path integral, but of course when you rotate to Euclidean time, it becomes minus SE. And so you'll notice that the Euclidean action is actually negative for this case. Now, we're going to do a bit better because we're going to include radiation in the calculation. There's a subtlety because, of course, the real cosmos is very far from equilibrium. One can consider de Sitter space-time as to be in a kind of equilibrium. Nothing really changes for any observer in de Sitter space-time. But the real cosmos is very far from equilibrium. There are at least two temperatures. One is the temperature of the radiation, 3 degrees Kelvin, and the other is the temperature of the de Sitter space-time associated with this lambda. And these differ by 10 to the 39, so they're wildly different. So you can't describe the system as being at a single temperature. Secondly, for StatMech in cosmology is tricky because for spatially compact spacetimes, the Hamiltonian is 0 on all states. So you might wonder, how am I going to construct the partition function when the Hamiltonian is 0? And so the partition function is just a sum over all states. Nevertheless, you can still define a statistical ensemble, as I'll show you. And furthermore, a positive thing is that the expansion rate in the presence of this radiation goes to like the square root of the density of radiation times Newton's constant. And that is way smaller than the temperature of the radiation. So the evolution of the space-time is slow compared to the timescale in the radiation itself, which is just determined by its wavelength. So expansion of the universe is adiabatic. So it's a very good approximation to treat the radiation as being in local thermal equilibrium, and just to integrate out the microscopic degrees of freedom, photons, electrons, protons, and treat it as a perfect fluid. And that's what we do. Now, let's talk a little bit about path integrals. This is another area of my research, trying to define these properly. And so I've thought a lot about this. You know, the path integral is king in physics, in fundamental physics, or I should say it's the emperor. But in fact, the emperor has no clothes because no one actually yet has a precise definition of a path integral. It's an infinite dimensional, extremely oscillatory integral, and nobody can tell you whether this integral actually converges or exists or anything. So that's a very fascinating topic. Our approach to it is based on the results of Picard and Lefschetz, who gave a general procedure for dealing with oscillatory integrals in finite dimensions. We are generalizing it to functionals. But the theorem is the following, that the magnitude of this integrand, if the magnitude is less than or equal to 1, and it certainly is for physics path integrals, then it follows that the real part of IS at any saddle is less than or equal to 0. It is simply mathematically inconsistent to consider saddles which have negative Euclidean action. Okay, that is the case for transition amplitudes. And we realized this and published a whole series of papers disproving the Hartle and Hawking proposal for the wave function of the universe. However, if you're not talking about amplitudes, but you're talking about statistical physics, that's quite different. The partition function is a trace over all states. And as I said, in gravity, the Hamiltonian is 0. However, you know that for geometrical ensembles like polymers or strings or membranes, the entropy, and this partition function, it depends on the entropy in this way. And by the way, the energy term is 0 if the Hamiltonian is 0. So the partition function is e to the entropy. And for these geometrical objects, the entropy is exponentially large. So from this point of view, it's not at all surprising that a semi-classical, that a saddle point to the path integral has to have positive Euclidean action. Okay, so there are these two different cases which have not been properly distinguished in the past. So we're interested in this case. We want to study the statistical physics of a space-time, and we're going to be looking exactly for a semi-classical saddle. Now, as I mentioned, the radiation is in local thermal equilibrium, so it makes perfect sense to integrate it out first. You split the total Hamiltonian into the gravity Hamiltonian plus the radiation, and in the lowest approximation, the gravity one is only going to depend on the scale factor of the universe. One can generalize that by including perturbations, and we will do that. But in the first approximation, Hg is an operator depending only on A, the scale factor of the universe. And very fortunately, in the approximation that the radiation is conformal invariant, which it is to a certain order in perturbation theory, this Hamiltonian is completely insensitive to A, doesn't it? Just decouples. So we treat it as a conformal invariant at a certain temperature, and we do the trace over the radiation first. Now this trace is easy to guess just from the formulae I gave. It's equal to the exponential of the total entropy in the radiation minus beta times the energy density in the radiation. Now this is very important. The total entropy in the radiation in the universe is adiabatically conserved. And that means to very high precision, this is a constant, it's a number. And it depends on the total volume of the universe. It's roughly speaking the temperature cubed times the total volume of the universe. That number will be crucial. So even though we have this paradox that H is 0 on all physical states, we can treat HR as a constant, and that will be our control parameter for this non-equilibrium statistical ensemble, because we integrate out the radiation, and then we write down the path integral for gravity. So what happens is the Hamiltonian for gravity comes in, and this UR comes in this way. Now, the way I get this formula is by analytically continuing in beta. This is just a totally standard formula, but I analytically continue in beta. Beta is IN, N is the lapse in GR, and this integral now imposes the constraint that the total Hamiltonian is 0. So, which it should be on all physical states. So you see we've introduced a parameter into the ensemble which will be crucial, and we are imposing the constraint that the total Hamiltonian is 0. Well, now we can transfer this into a path integral for cosmology, and notice it does have an I because of this.
Sorry, Neil, only
yes.
3 minutes left. Sorry.
Okay, no, that's fine. Okay, so it has an I. Even though I'm doing StatMech, it has an I because you're imposing a constraint. Okay, so now it's fairly straightforward. This is the action, just the usual action for cosmology. All cosmologists will be very familiar with this. Here are all the solutions. In view of time, I won't dwell on them. All I will say, let me see. I just want to explain the notation. A is the scale factor, N is the lapse. It turns out there are two ways to go Euclidean and to get a positive exponent. One of them is the usual Wick rotation. Another one is what we call CW. It's a conformal and Wick rotation. You rotate the lapse and the scale factor. It turns out the Wick rotation only yields instantons for small radiation density, less than the Einstein static universe, and for positive curvature. Whereas this new rotation, which is what we do, gives instantons for all parameters, provided lambda and r are positive. So we have new instantons. They give the entropy of the universe for all cosmological parameters. Let's see, Latham has already mentioned this A of t. Here is our picture of the two-sheeted universe. The new thing in our instanton is that we allow the scale factor to have a simple 0. We allow it to have a conformal 0, and we allow these poles, which are the future, asymptotic future of de Sitter spacetime. And then we have boundary conditions at the bang, which are what we call an analytic mirror. The Big Bang is literally a mirror. There are two sides. They are mirror images of each other. Latham already showed this. The scale factor is doubly periodic in the complex plane of its argument. And this is very useful in order to calculate the Euclidean the action for the Euclidean instantons. Just wanted to mention one point. We actually require the lapse to be, the Euclidean lapse to be positive for the matter. That's when we integrated out the radiation, and to be negative for the gravity. And in the way in which we do the path integral, this is absolutely fine. You do it in 2 steps, and what you mean by the trace over states is different, and this is how you reconcile non-equilibrium, the non-equilibrium situation. The lapse uses, the matter uses 1 Wick rotation, and the gravity uses another. Or mathematical physicists have long believed that the Euclidean picture is fundamental of path integrals, and there's some very recent interesting papers on this. In the Euclidean plane of in the plane of the Euclidean lapse, they would say only the right half plane is allowed. Unfortunately, I think they got it exactly wrong, because the Lorentzian one is fundamental, so they capture only half of the physical lapse plane, and basically we do 1 rotation to Euclidean lapse for the matter, and then we do another one to negative Euclidean lapse for the gravity. Here are the instantons, and here's the final result. This is the gravitational entropy divided by the entropy associated with de Sitter spacetime. It's just a convenient unit. And the parameter is the entropy of the radiation, the total entropy in the radiation. And what you see is that if that entropy in the radiation exceeds a certain number, so today S lambda is about 10 to the 120, SR is about, the entropy we can see in the radiation is about 10 to the 90. So this number, I mean, in just the part of the entropy we can see is about 1. But, and this is not counting black holes and matter. We still have to do that. But this is a convenient unit. And if it exceeds, if this entropy in radiation basically gets substantially bigger than the stuff we can already see, to that extent, the total gravitational entropy gets bigger than the de Sitter entropy. And one can show that the omega in the curvature, the importance of the space curvature in the Friedmann equation compared to the radiation lambda, declines. So if the total entropy is bigger than 1,000, universe is flat to better than 1%. And that's extremely plausible. How do we know the universe isn't bigger than 1,000 times what we can see? So there is also an understanding in terms of horizons. I won't go through that, but one can see the scaling just by counting the number of de Sitter horizons in the universe today. And if the 1,000 of the volume we can see, then the most probable omega in curvature is less than 1%. It's just the same with the Earth. If the total atoms in the Earth exceeds 10 to the 42, and we could have probably told you that thousands of years ago if we knew about atoms and gravity, for sure we would know this, then we could infer the diameter is bigger than 100 kilometers without doing any measurements. And this calculation convinces me that actually it's not implausible at all that the universe is finite, and it's just a factor of a few, maybe 10, maybe 100, bigger than what we see today. We've also done calculations for all the perturbations. They increase the Euclidean action, hence decrease the entropy. Hence, the most probable universe is homogeneous, isotropic, and flat on large scales. There's no need for any mechanism to explain these properties. Now, that's not to say everything is done. As much remains to be done. We have to generalize the non-conformal invariant matter and to include black holes. We don't see any roadblocks there other than technical difficulties. We have to explicitly construct the quantum ensemble and show that our instantons are relevant saddles. And then we have to rigorously construct real-time path integrals, and that's what we're in the process of doing. Now, I just want to mention at the end this connection with holography and ADS-CFT, which we've only very recently appreciated, and this is work with Malcolm Perry. there's a beautiful 1+1 analog model for this whole thing, and it's just a string moving in an antisymmetric tensor background, a constant antisymmetric three-form field. It's just the analog of the Schwinger problem, but for a string instead of a particle. The equations of motion are the following. You find well, the induced metric on the world sheet is conformally flat. It looks just like cosmology. And furthermore, it's kind of a miracle, the equation for the scale factor, which is just the size of the string loop, turns out to be identical to the equation I wrote down for A. So all the same Euclidean instantons apply. One can compute the entropy for this 1+1 dimensional universe, toy universe, and then we can actually check this model happens to be exactly solvable, and we can actually count the states and check those formulae for the entropy I showed before. So that's very exciting, and I think this will add increased rigor to this approach. So thank you very much for listening.